Thank you for the introduction, Nick. Good morning, I'm Chorong from KAIST Korea. Today, I'll talk about at pre-installation time, how we can provide the personalized power information of continuous sensing applications. This is a joint work with Singapore Management University, Korea Tech, IBM Research, and Naval Labs. Recently, a number of continuous sensing applications have been proposed. In the background, they continuously monitor our diverse contents, such as physical activity, transport mode, conversation, and sleep quality. Despite much effort for energy saving, we all know that these services consume much power due to much efforts due to the continuous sensing. But according to our previous work in this year's RubyConf, we found that users, they have a very limited understanding on sensing applications, continuous operation, and battery impact. So they just install and use these applications, and they often get embarrassed due to unexpected battery depletion. Of course, before installing the application, we can see some power-related information in the application market. Some developers report the expected battery use in the description, like it'll be fine if you charge your phone nightly. Also, some users leave comments about their battery experience. But these are not that practical yet. In many cases, the description is very ambiguous, and also, the user comments are inconsistent. These two comments, the right ones, these comments are from the same applications and around the same time. The upper user complimented its acceptable battery drain, but the lower user was furious about its battery. Also, even though the developers tried to accurately measure the power using power monitor, we found that it cannot be accurate. Before installing the sensing applications, what if you can see the personalized and detailed battery use information of the continuous sensing application, like this? Think about you can compare the expected decrease of battery life for several applications. Also, you can see the estimated battery use over days or over time. If this is possible, you can be relieved exhaustive trial and error to find an energy-efficient application. However, it's not easy to realize such a function in reality. We found that one of the most important reasons is, even for the same sensing application, its power use varies largely from person to person. To quantify the difference in real life, we developed a conversation monitoring application, and we analyzed its power use from 27 users over 3 weeks. For the power metric, we measured how long a conversation monitoring module was performed. Surprisingly, its daily duration was quite different from person to person. The standard deviation was around 2 hours, and the top user activates more 3.5 hours than the average user. Why does the same sensing application make different power use like this? We found that one key reason is diversity in individual user behavior, that is, physical user activities and phone use patterns. Why do such user behaviors affect the power consumption of the sensing application? First, sensing applications often adopt conditional sensing pipeline for energy saving. In the previous example, the application performed the conversation monitoring module only when a user was with somebody. The second reason is resource sharing. Sensing applications mostly run in the background, and thus they often share the hardware resources with foreground applications. As you already know, the wake clock cost is almost zero if the other applications acquire the wake clock. Such resource piggybacking is on the smartphone was already introduced by Ning Lane here in SenSys 2013. So due to the resource sharing, interestingly, the power increase of sensing application will be smaller for people who usually use the phone longer. So we built PowerForecaster for the personalized power estimation. As a system input, it takes each user's specific behavior, and the application is executable. And it provides the personalized power impact as an output. We built PowerForecaster with 5 design goals. Most important, it provides personalized power estimation tailored to a specific user behavior. Install and run the application on their smartphone. Estimation result in a short time and minimizing the overhead on by their application binaries. I go through. To enable our grand idea to provide the power information to the application market, many components are necessary. In this work, we focus on accurately estimating power consumption with the collected user behavior traces. So for the purpose, we devise a user behavior-aware power emulation approach. The idea is simple. Instead of running the application on a user's smartphone, we emulate the application's power use on the cloud side. How can we produce the power value on the emulator? We track the hardware usage of the sensing application and map the usage to the power value using the power model. For hardware usage tracking, we need to execute the sensing applications on the emulator. So to guarantee the sensing applications as if it runs on a user's smartphone, we record the sensor trace on the mobile side and replay it on the emulator. Also, to consider the resource sharing, we collect the device usage trace made by the existing applications and replay it on the emulator as well. Okay, so the first step to enable this approach is to collect the sensor trace and the device usage trace on a user's smartphone. I first explain the sensor trace collection. What type of the sensor information do we need in order to account the power consumption of the sensing application? Of course, the essential one is the sensor data streams with the timestamps. Is it enough? For the ordinary emulation, maybe yes. But for the power emulation, we need 2 more types of sensor information. First, it's sensor device-related system calls. They are needed to reproduce the power states in the sensor device. For example, the time to activate the GPS largely depends on whether a user was outside or inside. So we can reproduce such an environment by replaying GPS start and GPS stop functions as if they are made on a user's smartphone. We further record the sensor-related system events, like GPS event started or GPS event stopped. Many applications and the Android framework use these events as a trigger of an internal logic. Next, let's move on to the device usage trace collection. Let's first think about how we can consider the power use and the corresponding resource sharing of the existing applications on the emulator. A naive method would be to install or use the application on the emulator and execute them based on the input of the applications. For example, we can execute the Facebook application on the emulator by replaying all the user interaction and the network usage. But as you expect, it's not a good solution. It requires heavy computation, and it's very challenging to log and replay the realistic inputs. So we take another approach. We record and replay the requests to the hardware components. Actually, from the perspective of the power estimation, which application is running is not important at all. The important information for the power estimation is which hardware components are being used. So for example, if we know when the Facebook application acquires and releases the wake clock, we can easily consider the wake clock sharing with the Facebook, even without the actual execution of the Facebook application. This table shows the request APIs and the parameters for the representative resource types. Okay, so we examined what we record for the sensor trace and the device used trace. So what will be the next question? Many of you may be concerned about the power cost on a user's smartphone. Actually, we do not collect these traces for every power request. These traces collected once and they are used for general sensing applications in the PowerForecaster system. So we collected the traces for 1 to 2 days, possibly for one weekday and one weekend. But it's not enough yet. Recording the sensor data all days is a still battery problem. And even though we perform it only 1 to 2 times. So we applied widely used duty cycling techniques. Human contacts like mobility, location, encounter, they have a high level of temporal locality. See, here most of you keep sitting more than 1 hour. So a practical issue in adapting to such duty cycling techniques is how far we can increase the cycle while minimizing the accuracy decrease. And to answer the question, we analyzed the power use of a location tracking application with 2 18-long traces. In the graph, the blue box means the power cost for the data collection, and the purple circles means the error rate of the power estimation accuracy. We can see that the ratio of 1/12 shows a reasonable performance. The power estimation error is still below than 10%, and the power cost starts to saturate. Let's move on to power emulation. Upon a user request, how can you calculate estimate the power consumption of the sensing applications with a collected trace? And this is the architecture of the user behavior or power emulator. We developed this emulator by significantly extending the existing Android emulator. It has 4 key components: the sensor emulator, hardware usage monitor, device usage replayer, and power estimator. The power estimation process consists of 3 major steps. First, the sensor emulator mimics the physical sensor device to fulfill the sensing application request. It feeds the sensor data and emulates the power state of the sensor devices. Second, the hardware usage monitor tracks the system calls made by the emulator to use hardware components. Then, after the emulation, the power estimator computes the power consumption of a sensing application. And in the calculation, we account the shared use of resources to accurately estimate the additional power of the sensing application. Let me quickly go over key operations in a bit more detail. Before introducing the sensor emulation, I'd like to ask you something. I think many of you have experience on the Android emulator. So can you guess what happens if we run the commercial pedometer on the Android emulator? Actually, I installed and run this application on the emulator, and I recorded the emulator. And see? Yeah, nothing happens. What you're seeing is not a stream image, it's video. But it does not execute anything. So now I show you what happens on the PowerForecaster with the sensor emulator. The sensor emulator feeds the sensor data in the background, and as you see, it updates the stack count. That means the emulator executes the sensing application. Here, I briefly describe the sensor emulation with the location tracking application and the GPS example. Upon the location update, the GPS emulator feeds the GPS data based on the collected GPS trace. At the same time, it broadcasts the system events like GPS events started. While feeding the data, it also mimics the internal operation of the GPS device. For example, it calls the GPS on and GPS off function according to the interval collected in the trace. So if a user was outdoors at the time, in the left example, GPS off function will follow immediately. And while feeding the data, it also hooks the system calls made to the kernel and notifies them to the hardware usage monitor. I'll explain how we estimate the power with such a system calls in the next slide. Besides GPS, we also developed the sensor emulator for diverse sensors, including accelerometer, gyroscope, Bluetooth scan, and Wi-Fi scan. So the next step is to estimate the power consumption with the collected system calls made during the emulation. After the emulation, the hardware usage monitor returns a collection of system codes. Here's the example. So for the power estimation, we adopt a finite state machine-based power model. This model was proposed by Abhinav Pradhan in EuroSys 2011. For power monitoring, we consider diverse hardware components, including inertial sensors, GPS, Bluetooth scan, and Wi-Fi scan, and microphone, and so on. And these models are the example models made based on system calls for GPS and Bluetooth on Nexus S phones. Such finite state motion-based models facilitates to consider the tail power state of each hardware component and the sharing effect across the system calls. So finally, we construct a finite state motion for the entire device, and finally output by applying the sequence of the system calls to the phone-wide model. According to our measurement, our power model achieves around 93% of the power estimation accuracy. So the last step for the accurate power estimation is to account the shared power use with existing applications. For the purpose, the device usage player replaced the device usage trace to consider the existing applications the hardware sees. So the output from the hardware usage monitor is the phone-wide application usage, not the sensing application-wide hardware usage. So to accurately estimate the power cost of a sensing application, we need to isolate the power used by the sensing application. In this work, we take the account policy that only accounts the power cost while only a sensing application uses the resources. For the power cost while resources are shared with existing applications, we assume this is solely due to the existing applications, which means no power cost by the sensing application. To quantify the effect of this accounting approach, we compare the performance of the estimation between when you consider the shared use and when we don't. And with the workload used in the evaluation, the error comes up to 46% on average if we do not consider the resource sharing. Okay, until now, we see how to accurately estimate net power increase of an application using our power emulator. However, we still have severe and more challenging. Guess what it is? It's a long emulation time. To reflect a user's real-life behavior in power estimation, we need to consider at least 1 day or half-day long trace. Since the sensing applications operate closely tied to the physical real-time clocks, so the naive emulation takes the same duration of the sense traces. That means you may have to wait for 1 day to see the power information. If so, nobody will use this service regardless of the utility. To address this, we developed 3 acceleration techniques: parallel execution, idle time skipping, and progressive estimation. Let me show you how well these techniques work first. This graph shows how fast you can provide the power estimation without much error. X-axis represents the time when the power estimation was made, and Y-axis is the error rate when we apply all the acceleration techniques. Surprisingly, for occupied and MyPath case, it takes only 20 seconds to reach the error rate under 10%. For German case, we need relatively more time to reach 10% error, but except one outlier case, it takes only 10 seconds for 5% error. Now, I'll explain more details about the acceleration techniques, but due to the time limit, in this presentation, I will present the idle time skipping only. Idle time skipping leverages the unique characteristic of sensing applications. For energy saving, they try to keep device in the sleep state as long as possible. So for example, the occupied application, it wakes up every 10 seconds to detect the user's movement with 20 millisecond accelerometer data, and sleeps again if there is no movement. So this technique shortens the emulation by detecting and skipping the idle time. In the occupied example, it can significantly shorten the emulation while a user is not moving. Please see our paper if you are interested in the implementation detail and other two techniques. Okay, with the prototype system, we performed diverse experiments in the realistic map setting as well as real deployment. The evaluation metric is the power estimation accuracy, and we also examined the system overhead. For the evaluation, we used two smartphones, Nexus S and Nexus 5, and 5 sensing applications, 3 commercial pedometer applications, Occupedo, Numok, and Pedometer 2.0, and 2 research applications, MyPath and Chenmon. For default setting, we used Occupedo, MyPath, Chenmon on Nexus S phones. As another important input of the PowerForecaster system, we crafted 5 1-hour user behavior scenarios. We consider 4 major parameters: mobility, indoor-outdoor status, encounter, and phone usage. And we determined the parameter values from the real user data we used in the motivation study in the beginning. And this is the detailed sequence of the user activities and phone usage behavior for scenario 4. We made other scenarios similarly. For the estimation and the comparison, we used 4 phones and 3 power monitors at the same time. First, PowerForecaster. We collected the sensor trace and the device usage trace from a single phone, and we emulated the sensing application's power use with the collected trace. For the ground truth, we measured the power values from 2 power monitors, one for sensing applications and foreground applications, and the other for the foreground applications only. Then we take their difference as the ground truth. And for comparison, we consider the development time measurement. We call it global average. It measures the power consumption of the sensing applications, all 5 scenarios, and take its average as an output. But it doesn't consider the resource sharing, because we think it is hard to consider the user's phone usage at the development time. And in the experiments, it is critical to ensure the same user behavior over various alternatives and different phones. So we designed a versatile setup to easily conduct multiple experiments. On a cart, we installed multiple phones and power monitors, laptops, and high-capacity battery with 40 ampere. With a cart, we carried these devices at the same time and in the same way. Okay, let's see. For 15 test cases with 3 applications and 5 scenarios, PowerForecaster shows 7% of an average error rate. And unlike PowerForecaster, the global average shows much higher error rate, 99%, even though it considers all the scenarios and takes its average. And this shows that the importance of the personalized estimation with a specific user's behavior trace. Let's see the result in more detail. The below graph is the result of the Occupedo application. The leftmost blue bar is the ground truth, and the red one is the PowerForecaster. And we can see PowerForecaster provides the accurate power information for all scenarios. I skipped some results for the time, and I briefly described the result in the real deployment. To evaluate the performance of the PowerForecaster in the real deployment environment, we recruited 7 participants, and we provided a Nexus S phone. We asked them to install their own SIM card and the applications they usually use. So then we collected that data for 2 weeks. In the first week, they usually use their phones as usual. And when the second week started, they installed one of the sensing applications. We first measured how long the battery decreases in the second week due to the sensing applications. As you can see with the graph, even for the same sensing applications, the battery impact was different depending on the participant in real-life situations. For example, for Occupedo, the decrease in battery life ranges from 5 hours to 15 hours. And this is the estimation of the PowerForecaster with 2 days that the participants picked. So as you can see in the graph, for all 14 trials, PowerForecaster shows 90% of accuracy for 10 cases. Of course, there was a few cases that the estimation was not that accurate, but according to our interview, it was the irregular behavior of the participants. Okay, last. Beyond providing a single power value, PowerForecaster can also provide the diverse power information with respect to user context. This shows the expected power hotspots of the participant 4 for the MyPath application. Last, I briefly mentioned the system overhead. For one-time collection mobile side, the battery decrease is only 1.1 hours for Nexus S if we applied 1/12th duty cycle. And for the server-side cost, for one-time emulation, the overhead is only 5% of CPU utilization and 400 megabytes of the memory. But the memory workload is mainly from the loading virtual phone image. Last, I just mentioned the limitations in our future. I think we can provide more personalized estimation by representative user behavior traces. And also we need to deal with the server-side scalability for the worldwide scale services. And as you know, we need to build the power model specific to the individual's phone models. So we'll adopt the self-constructed power models. And let me conclude my talk. In this talk, we uncovered that user behavior is the key to understand the power impact of content sensing applications. And by leveraging this, I proposed the PowerForecaster, the system to provide the personalized power information at the pre-installation time. Thank you. I'd be happy to take any questions.